Okay, hello everyone. So we were discussing how to generate electricity using magnetic fields. Now you know that if you place a coil, a conducting loop in a magnetic field, so here's magnetic field and here we have a coil full of wires, and then we have some mechanism to rotate this. So let's say we rotate it around this axis. And then we also have mechanism to take the current out, some kind of mechanical arrangement for that, and we can connect this to a bulb, something like this. So when this thing rotates, it will produce electricity. It's given by voltage equals negative n flux change over time, or using a little bit of more math, we can say equals negative n d psi by dt. So we can find the amount of voltage it produces, depends on how many turns there and how fast the flux is changing. Now the flux psi is dA cosine theta. The maximum is sine max is just BA, but at any given point, depending on what is the angle this coil makes with the magnetic field, is given by BA cosine theta. So the things we know so far: the faster it rotates, more electricity. Stronger the magnetic field, more electricity. More flux means the magnetic field and the area together, more electricity. And then depending on what kind of resistance this circuit has, we can figure out what the current flow in the circuit. Okay? Alright. So in a practical application, now this diagram to the right, we call these things electrical generators, or sometimes we say dynamos. Now here's somewhat of a kind of a practical application. Here you see that there's two magnets, and in the middle there is this one loop of wire wrapped around some kind of a cylinder. It's rotating. In this case it's going clockwise. The axle is rotated mechanically, and then the wires, as I said, they don't have these permanent connections, right? We call them slip rings and brushes. So it's not like a rigid permanent connection. They touch each other. That way you can have electricity coming out, but that doesn't twist the wires. That goes into a light bulb, or we can put it into storage devices, or whatever you want to do with it. Now, how do you find the amount of electricity coming in a real generator, depending on how fast it's rotating? The rotational speed can be expressed in a couple of ways. One is to mention the frequency. Number of cycles per second, right? Frequency is given by hertz. If it says the frequency is 10 hertz, that means this coil is rotating 10 cycles per second. Another way is express it in terms of omega, angular velocity or angular frequency. Omega, angle per second. Angle rotated in a unit time, or rotated per second. So radians per second, that's the unit. Omega is angle, theta, divided by time, but angle should be measured in radians, not degrees. So this is another way of stating the speed it's rotating, right? There is a relationship between these two. Omega is 2 pi f. So that is also something important. Omega is this. Here's the definition of frequency, and this is how we connect omega to frequency. In our household electricity, frequency is, you might have noticed this, it's between 50 to 60 hertz in US and in many countries. That means these generators in actual power stations, they all have this standard. They all rotate at the same cycles per second, so that everybody gets same kind of electricity, right? So it is important because when you design equipments to use that electricity, like washing machines, refrigerators, microwave ovens, they should match that incoming frequency. So it's a worldwide standard to keep the same frequency. Okay, so we know that the amount of voltage depends on N and delta psi by delta T. Now we also know that, let's write it here, N delta BA cosine theta over delta T, right? Instead of psi, I'm going to write BA cos theta. Now using some little bit of more mathematics, we can show that. Now here, if you take a look at it, B is a constant. In an actual generator, the magnetic field remains the same. If you look to the right, it's two permanent magnets. They don't change, so the magnetic field remains the same. Area of the coil remains the same. It's the coil wrapped around this cylinder, so that doesn't change. Area remains same. So what changes here is the angle that area makes with the magnetic field, because it's rotating. Sometimes it's perpendicular, sometimes it's parallel, sometimes in between. So the only thing that changes here is theta. Theta also, if you look at this equation over here with omega is theta over t, so therefore we can say theta is omega t. Now you see that this theta, the angle, has some time dependence in it, right? If we rotate this thing at the same speed using some kind of force like a wind turbine or water turbine or something, if we rotate it, if we maintain the same speed, angle changes with time. So there is a time dependence in it. So at every moment, the angle slowly changing. So we can go another step and say negative n, B and A also constant. It's only cosine omega t over delta t. So this is the only part that changes in this equation. The same version, same thing in calculus, we can say equals negative NBA d cosine omega t over dt, taking the derivative of cos omega t in terms of time. Now, we can solve this equation. You guys who have taken calculus, you know what to do with this. Next step. We can do the same thing here. So finally, let's go to the answer. Let me go to the next slide. And let's clear this. We can finalize and say that voltage produced is equals to NBA omega sine omega t. Oops. Undo sine omega t. This tells you how the voltage changes when a coil rotating in a magnetic field, number of loops n, magnetic field A, area of the coil, how fast it's rotating. All these things are, all the first four terms are constants. The only thing changes is this part, the time. So you see that it is a constant and the sine part, right? So what we have is, if you plot the electricity it produces against time, what you get is a sine wave like this. Now in this sine wave, what is the maximum? The sine maximum for a sine angle, max it can get is 1. So therefore, maximum is NBA omega. So this graph, the voltage it generates goes to a maximum of this Emax and a minimum that is also Emax but negative, and it oscillates between, right? It goes to a maximum, comes to 0, goes to a negative maximum, comes to 0. That means the direction of the current, negative voltage means current is going in the other way. So this is an AC generator. What we have here is an AC generator. Current goes back and forth, oscillates between two maximum values. And this is the maximum, so you can again, if you want to write this, E equals E max sine omega t. But you need to remember here, college physics, maximum you can produce using this. University physics, you guys need to know the entire equation. Alright. So this is the function of a generator, AC generator. Electricity goes back and forth. If you go back to the previous slide, pay attention to this arrangement. These are called slip rings. The wire comes from the coil, goes to a ring. The ring is attached to this cylindrical shaft. So the ring rotates with the wire. The other wire also attached to another ring. So these rings are fixed. They are rotating with the cylinder. And then these brushes. So the brush is in contact. It's touching these rings, right? So ring can rotate, but electricity can still pass to the brushes, goes in the cycle. So in one half cycle, the current goes in one direction. The next half cycle, it goes in the other direction. That's why we call it AC, alternating. So this is this. So let's give a try and let's try this math problem. The armature, that's the rotating part of a 60 Hertz AC generator. So give it a try. Frequency 60 Hertz. Magnetic field 0.15 Tesla. Area of the coil 2 times 10 to the negative 2. How many loops do we need if the peak output is to be some percentage sign which we don't need, to be 170 volts. Let's just say we want the peak to be 170. That means this peak over here needs to be 170 volts. That means E max has to be 170. So E max needs to be 170 volts. So NBA omega needs to be 170. How many loops? That's the question. N times 0.15, 2 times 10 to the negative 2, times omega. Now let's find what omega is. Omega is 2 pi f, 2 pi times 60. So 2 pi times 60 should be 170. That is N. Okay, let's take the calculator. 170 divided by 0.15 divide by, I'm going to pause this. Okay, I get 150.313. Now these are number of turns, so we should round it, and you can just say it's n equals 150 turns. So this coil should have 150 loops, 150 turns, and if it rotates at this speed, this kind of magnetic field, it will create a maximum of 170. So the voltage comes out, goes like this, between 170 and negative 170. Later we'll discuss that in AC voltages. Now this is going back and forth, but we take an average, and that's what we call the actual average voltage. Now if something goes between negative and positive, equal negative and positive, it looks like the average is 0, right? If you just add 170 plus negative 170 divided by 2, you get 0. So how do you get the average of a sine wave? You might have learned this in your math classes, right? How to get the average of a sine function. We take something called the RMS value. Now, you won't get these things in the exam, and I'm just adding these for your knowledge. RMS value, the root mean square value. So when you have a sine wave or a cosine wave, what you do is root mean square. Actually the operation is backwards. You square it. So when you square a sine wave, it gets bigger. The negative part also, when you square it, it becomes positive. Like this. And then you take so that's the squaring. You take the mean, or you take the average of this. Right? You add them all together. Now it's all positive numbers. You get the mean value. And then you take the root of it, square root of it. So you bring it back to what it was. So that's the operation, RMS value. Now if you do the RMS for this, there is a technique how to do that. It comes to about 110 volts. This is what we call the AC voltage, 110, 120 volts. That's the AC voltage of United States, right? Some countries have 230. So the idea is this voltage oscillates back and forth between these two peak values. We take an average and RMS value, and that's what we say the voltage is. In reality, it goes back and forth like this. Okay, so that's the answer to the problem. Let's move on. A DC generator, on the other hand, it's similar, except that it has split rings instead of slip rings. So there's a slight change in the word, but that makes a big difference. A split ring, the first diagram. So this arrangement makes sure that current doesn't flow in back and forth manner. Inside the coil, it goes back and forth. But because of this particular arrangement, now the coil has two wire ends. One end is connected to a half a ring, that's a split ring. The other end connected to another half a ring. Previous one has two solid rings. Now we use half rings. They goes into brushes. So that way, every time when the current changes the direction, the point that it comes out into the brush also changes. That way, outside the coil, in the circuit, rest of the circuit, it goes only in one direction. It doesn't go to the negative side. So it makes this half cycle kind of pattern. Now over here, in a more practical motor, here you see this is just a one coil. I don't know whether you can follow the pointer, but it's just one coil. Over here you have multiple coils in different planes. So this half cycle, so with one coil, it like this. But with multiple coils you can overlap. something like this. And the end result is something with more steady current, more steady voltage. Okay, that's the idea. All right. Okay, so let's finalize this. A coil rotating in a magnetic field is an electric generator, produces electricity, and the shape of the electric current that comes out, that generates the voltage, is a sine wave. It takes the shape of a sine wave, goes between two maximum and minimum points. The maximum that it generates given by this NBA omega equation. So you can see more number of loops, more magnetic field, more area, faster rotation generates more voltage. And depending on how it comes out from the coil, depending on the connection, the type of the connection, slip rings makes it AC, means the current comes as it produces inside the coil. Split rings makes it DC. So it prevents current from going back and forth, and it puts into a unique one direction. So a little bit more details, we might go over these later in the semester, but I'll just talk about it right now. So let me clear this. So we have AC, which is back and forth, and DC, which is unidirection. It goes to a peak, comes to zero. It doesn't go to the negative side. So this is electricity over here, electricity, and this is time. Now, there are advantages on both of these types of currents, right? Certain instruments do need AC. Certain instruments, they don't care whether it's AC or DC. Like, for an example, a heating element. It doesn't matter the direction of the current flow. As long as there is some movement back and forth, when this current goes back and forth, the atoms inside oscillates back and forth. That generates heat, and that's all it needs. Right? A light bulb, an old-fashioned light bulb. We call them incandescent light bulbs. What it needs is some electricity inside that heats up the element. It starts emitting light because of the heat, so it really doesn't care the direction of the current. AC has some other advantages. AC is easy to convert into, like, if you want to change the voltage, let's say the generator produces something like 170 volts. But for your household appliance, you need only 12 volts. So these kind of transformations, we say the average is 110 volts, okay, the average. You want an average of 12 volts. So these kind of transformations are much easier when the voltage goes back and forth. DC has its own applications. Mostly sensitive electronic devices needs unidirectional voltage or unidirectional current. So we have to go with DC. So that's one thing. The other thing is, now here the DC that comes out from the motor, from the generator, we saw that in one of those, in the diagram to the right on the PowerPoint, you see that it's an overlap of multiple waves, so it's something like this. Even these little ripples, we can straighten them out, make it a very nice uniform DC voltage by using some electrical components that we have studied before. The capacitor, so let's say here comes, here's the generator. So generators, in circuit symbols, generators are denoted by a circle and a letter G inside. That's a generator. Or sometimes this inside, That's an AC generator, circle, and this a DC generator, right? So let's say here we have the generator. Let's say this is a DC generator, so what we get is something like this. So the current comes in. Now here we have some kind of an equipment which needs, like your cell phone or the laptop, which needs a very uniform, smooth current. So what do? We put a capacitor over here, parallel to the component. So when there's the voltage, when it is changing, when it is increasing, it charges the capacitor. So in these ripples, when they are going up, when the ripple is increasing, it charges the capacitor. But during the second half cycle, so if I magnify this, it has something like this. When it is increasing during this half, capacitor gets charged. When it is decreasing, so the voltage across this also decreasing, but the capacitor will start pump some additional voltage and make it smooth. So over here it will be little bit of ripples, but over here it will be more uniform. So that is another purpose, another advantage or application of capacitors. They can straighten out changing voltages. One last thing, an AC generator, let's say this is an AC generator, produce a changing current like this, changing voltage. There are some methods without even using these split rings, using some electrical components, we can make it DC. There is a circuit component called diode. You might have heard this word before. LED, light emitting diode. Well, LED is a special type of a diode. A diode, a basic diode, it's a little circuit component, looks like a resistor, a little cylindrical device with two wire connections. The circuit symbol is this, a triangle and a line. Sometimes we put a circle around it. This tells you that current only goes in one direction. It's like a valve. It doesn't let current go in the other direction. This way it does not. That's what this line means. The arrow says it goes to the right. Line says it doesn't go to the left. This is unique. With any other circuit component, a resistor, current goes in both ways. Capacitor, we can charge it in both directions. It's bad for some capacitors, but still we can. So this is a gate to the flow of the current. These are made out of semiconductors, silicon and germanium semiconductors. You connect a silicon and a piece of germanium. There's a special way of doing that. These are called P-type, positive type semiconductors, and negative type, N-type. You connect them, you create a P-N junction. The junction allows current to go in one direction only. It blocks it from going the other way. So you put bunch of capacitors. I'm not going to go into so much details. There are different ways of doing it. Two diode circuits or 4 diode circuits. The process is called rectification. There's half rectification, there's full rectification. You can make this oscillating wave using bunch of diodes, bring it to this, like using a DC generator, and then you put the capacitor, make it more smooth, right? Okay, 30 minutes, that's it for this video.